So, ladies and gentlemen, let's move on from the last part of the video that we talked about the EPR paper. Now let's go back to the next part of this great debate that we have between Bohr and Einstein, and try to see the different formats that are appearing in this conversation where you have conferences going on and on. So what we have now is the Bell's theorem, the experiment that basically changed everything, and the argument, the mathematical argument that really astonishingly changed the course of quantum science and put its firm hands on its very strong foundation. So, ladies and gentlemen, welcome back. Welcome back to the continuation of the previous part. Now, what we have is we have now arrived at one of the greatest turning points in the history of physics, where there was an exponential rise in this field. Now, until now, what we have is the disagreement between Einstein and Niels Bohr. And this debate seems to be more philosophical in nature because there are philosophical arguments going on. Now we have what Einstein basically believed. Einstein believed that quantum mechanics was incomplete. On the other side of the debate, we have Niels Bohr, and Niels Bohr believed that quantum mechanics was complete. It was complete for Niels Bohr. So both sides had very powerful arguments. They had powerful logical explanations to disprove another's argument. But here was one more problem. But there was this one additional problem. No experiment basically could distinguish between Einstein and the arguments that were given by Niels Bohr. Now, on an average, nearly 30 years, for as long as 30 years, physicists debated this issue without any clear experimental path forward. It seemed more philosophical because there wouldn't have had the experimental support for these arguments. And many scientists eventually concluded that the discussion belonged to more, what we can say, philosophy than to physics. This was the majority of understanding. And then, as I said in the previous ending, it was in 1964, what we have this Irish physicist, and this physicist named John Stuart Bell, and he asked a question that no one had previously answered. And what was his question? What he asked? He asked, can we transform this philosophical disagreement between the two geniuses into an experimental test? This is what I said at the end of the previous video. And this question was revolutionary. It was revolutionary idea basically. And it was Bell who realized that Einstein's belief in hidden variables was not merely a philosophical argument. It was not a philosophical preference that was given by Albert Einstein. what it had measurable consequences. It could be measured. You could put a measurable consequence for this argument. Now, what was the argument? If hidden variables really exist, then certain statistical relationships between the measurements that you're making on should always hold. Now, if quantum mechanics was correct, those relationships would sometimes be violated. If you could ascribe those statistical relations between those hidden variables which are doing the job. This was extraordinary. And for the first time, nature itself could decide basically. And no amount of philosophical argument would settle. It would not settle the question. It cannot be argued in philosophical sense. So what happens here? You have only experiments. Only experiments could let us understand the Bell's idea, and using a simple analogy. Now let's try to go through it. Imagine that there's a company, and this company manufactures millions of pairs of gloves. If you remember, I talked about a pair of gloves in Einstein's framework. Now, each pair consists of a left hand and right handed gloves. You have a company, it's manufacturing millions of these gloves, these pair of gloves. Now, every pair is separated in two boxes. One box is sent to, Kashmir. One box is sent to Kashmir, and the other is sent to, now let's go beyond Delhi. The others is sent to, say, New York. Now, when you open your box in Kashmir and find left-handed glove, you immediately know that the box that has been transported to New York, you immediately know that the box in New York contains the right-handed glove. This is common sense, okay? And there's nothing mysterious here. Everything is clear, because before you could see the things, you know what was there. The gloves already possessed their identities before they were separated from each other. These identities were clearly known. This is the kind of explanation Einstein preferred. This was the explanation that Einstein was giving to this kind of paradox. It was a paradox in those times. The particles already possessed definite properties, and that's how you could predict about the nature of the rest of the particles who are leaving one group of particles. So what measurements are doing? Measurements are simply revealing them as the identities, as the particles. Now imagine something much stranger. Now suppose that before either box is opened, neither of the boxes opened, the glove somehow no definite identity at all. Only when one box is opened does nature decide the outcome. Even, even more, even more surprisingly, even more astonishingly, the other box immediately gives the correlated result. This is much closer to what quantum mechanics predicts, what mechanics predicts for entangled particles. And certainly Einstein found such a picture unacceptable. It was not acceptable to Einstein. He believed that hidden variables must already determine, they must determine every outcome. Whatever you are going to find out of these box, if you know these hidden variables. So what's happening? Bell realized that these two possibilities lead to different mathematical predictions. It was this John Bell. Now let's briefly discuss the mathematics only in the literal sense. No way, I'm not going to incorporate any equation here. I mean, don't worry about memorizing those equations. I'm not going in details of these equations. What matters is basically understanding the logic of these equations. And what Bell imagined two observers, and two observers performing measurements on pair of entangled particles. Now, each observer could independently choose, they can choose different measurement settings. Observer 1 and observer 2, and there are entangled particles, the particles have correlation. Now, if there exist hidden variables which are predetermined, hidden variables predetermined every outcome, and no influence, traveled faster than light, then the measurement results must satisfy a particular mathematical inequality. Now, today we call these relationships, these inequalities, we call these relationships as Bell inequalities. And the remarkable feature of the Bell's theorem is that it only needs, it only recurs a few very general basic assumptions. It does not depend on some detailed mechanics of any specific hidden variable theory. No, it's not like that. Its arguments are quite simple. Instead, it asks whether local realism can be true. Is the locality the true nature? Now let's define these two words. Let's try to understand these two words. Let's try to build some understanding on these two words. What is that? Locality. Locality means that an event is occurring here, cannot instantaneously influence another event that's happening far away, faster than that of speed of light, because we can put the limit as the speed of light. This argument is consistent. This argument is consistent with Einstein's theory of relativity. This is what locality means here in the framework of the Einstein special theory of relativity. Now the next argument is the realism. Realism means that physical properties exist with definite values before they are measured. It has a physical property, particle 1, and particle 2 has a physical property. These are the definite things that are living with these two particles. Einstein strongly believed in both of these arguments. The first argument is taken as locality, and the second argument is taken as realism. Now, Bell showed something astonishing. Now, if both locality, as I talked about, and realism are simultaneously true, then Bell's inequalities must always hold. They must always hold. They should never fail. However, quantum mechanics predicts that under carefully chosen experimental conditions, very carefully chosen experimental conditions, Bell's inequalities are violated. Now, if Bell's inequalities are violated, then localism and realism, they're both not workable. Think about the importance of this result. Bell did not merely, he did not produce, it's not like that, he did not produce another equation for relying on quantum mechanics. What he's trying to build is he builds a bridge between philosophy and experiments. You prepare your experiment. If you violate Bell's inequality, you violate realism and locality. And for decades, physicists had argued with words. And what happened? Bell replaced words with measurable physical quantities, with measurable quantities. Imagine two students arguing about whether a coin is biased. One student insists that coin is perfectly fair. There's nothing wrong with the coin. But another student insisted that it's biased. Now, instead of arguing whether student 1 is right or the student 2 is right, now instead of arguing, what they do, they flip the coin 10,000 times. The experiment settles the matter, whether the coin is biased or not. And Bell proposed exactly this scientific strategy. He proposed the scientific argument. Now let's understand. Let's understand the physical picture here. Let's understand. Let's build. Let's try to learn. Suppose two entangled photons are created. They are created together, and then they travel in opposite direction. One is, say for example, one is sent to a laboratory A, and another is sent to, say for example, laboratory B. So you created a pair of photons, you created a correlation between these two photons, sent them in opposite direction to laboratory A and laboratory B. Laboratory A may be separated by hundreds of meters or kilometers. At each laboratory, the scientists measure. They measure the polarization of the incoming photon. You have a scientist at laboratory A measuring the polarization of photon 1. You have a scientist at B measuring the polarization of photon B. Importantly, each scientist can freely choose the orientation of measuring the instruments, their own independent choices. Now, what about quantum mechanics here? Quantum mechanics predicts very strong correlation between the measurement outcomes. The two different persons measuring the photons in these two laboratories, laboratory A and laboratory B. Hidden variable theories based on this local realism predict weaker correlations. And these weaker correlations are basically constrained by the Bell's inequalities. Therefore, the experiment becomes straightforward. It becomes simple and straightforward, at least in principle. It becomes straightforward. Now, what's happening? Measure thousands of millions of entangled pairs. I started with the hypothetical argument of two photons. Now take it down to the millions of photons which are entangled pairs and compare the statistical results. If Bell's inequalities are always satisfied in every measurement, if Bell's inequalities are satisfied, Einstein picture will survive. It will live. It will have consequences. And if Bell's inequalities are violated, local hidden variable theories cannot explain nature. So note something profound here. Predict something profound is happening here. Bell's theorem does not prove that Einstein was wrong. It doesn't prove that Einstein was foolish. It doesn't do that. Quite the opposite. Quite the opposite. The Bell's theorem exists because Einstein asked the right question. That's the beauty of science. Maybe we could have never arrived at establishing these experiments without Einstein's insistence on clarity and completeness. Bell might never have had developed this remarkable analysis. It would have never come in picture. In science, even a criticism can become the foundation for revolutionary discoveries. And criticism is important in any framework of life. Now, many people ask an important question. And what's that question? Does Bell's theorem prove that faster than light communication exists? These are the questions that raise all along. And I believe the answer is no. Although entangled particles exhibit correlations that appear instantaneously connected. And these correlations cannot be used to send a controllable message faster than the speed of light, faster than the speed of light. The results observed at each laboratory remain individually random. They remain random. Only after scientists later compare their data through ordinary communication, through their respected communications, ordinary communication, these things do the remarkable correlations. These remarkable correlations become evident. Therefore, relativity's prohibition on faster than light communication remains intact. That remains as packed. This subtle distinction is one of the reasons quantum mechanics continues to challenge our day-to-day intuitions, challenges our intuitions. And Bell's theorem teaches us that nature does not. It teaches us that nature does not fit comfortably in our classical categories. Either locality, realism, or some other deeply held classical assumptions must be reconsidered. They must be taken into account. And this kind of realization basically transformed the foundation of physics. It changed the course of physics. And the next challenge was now obvious. And what was that? The next challenge, the mathematics. The mathematics was elegant, profound, beautiful, symmetrical. The logic was compelling. Come on, what's going on? It must be this way. It must act this way. But was nature truly consistent?